Welcome back. Let's conclude today's lecture with the proof of this easier transfer theorem. So recall what the easier transfer theorem said. Essentially, if we have an algorithm which is differentially private and an algorithm which is accurate in terms of the expected max of the discrepancy for any query is less than alpha, then we have that rather sort of on the data set, then we have that the max of any query on the overall distribution will be also bounded. And you note here we have an alpha, and here we have an alpha plus roughly epsilon plus delta. Yeah, this compares with the sort of more intense transfer theorem with because this one's an expectation rather than a with high probability guarantee. We'll prove this for the rest of the class, and the key lemma that we're going to have is the following one. This is kind of where most of the work is done, and then the putting it together and to conclude this will not be too hard. Now, essentially, this says the following. Let's read it. Suppose that W is an epsilon delta algorithm, and on input X, it outputs a counting query of some sort. Then we have that whatever this query is, then we have that if the data set is drawn independently, then we have the following guarantee that the difference between that query on the data set and the difference on that query on the on the distribution and on the data set, it'll be bounded difference in expectation. So this essentially says that the query chosen will generalize well. Yeah, it doesn't really say how yeah, it just tells us about, suppose we chose some query, privately, then it'll say that query is not going to go wrong. It doesn't say how accurately we estimate that query in particular using our algorithm M, which is also differentially private, but just says that we're not going to pick too unreasonable of a query. Okay, so let's see how we prove this. Yeah, we'll prove it on this page. So what we're going to do is we're going to essentially just use the linearity of expectation. So we'll use the following. So we start with expectation of Q of X. And just let me make clear that when I write this conditioning, it's not really so much a conditioning on this, but it's just sort of indicating where the Q came from. The Q is selected by this private algorithm W. So, okay, we have some query which was selected privately, and we run it on X, the data set. So this can be just written out by what the definition of the data set is. Summation of expectation of Q on Xi. I guess we'll use the notation Xi, where, again, Q is equal to what W picks on X. And this we can simplify to be equal, because remember, we're working in the restricted case where Q is a 0,1 valued query. It actually holds in more general settings, but we're just, for simplicity, looking at where Q is equal to 0 or 1 on something. So this can just be written as summation that probability that Q on Xi is equal to 1, given that Q is selected by W. Now, why did I change this from the expectation version into this probability version? Well, this might look kind of similar to something you've seen before in this class. In particular, we're just going to use differential privacy. So what we're going to do is we're going to imagine kind of what a neighboring data set is. Note that the kind of cool thing is that this quantity here for each term in the summation, it depends only on what Xi is, and it doesn't depend on the rest of the data set except in a differentially private way. So what we're going to do is we're going to define X prime I. This is going to be a new sample from the distribution, which is independent from everything else. And we let X prime be equal to the data set, which is let me actually write this capital X prime I, and the data set is going to be x1 all the way through xi is going to be replaced by this new sample all the way through xn. So you can see that this is a neighboring data set to x, where it's just x1 through xn. Now we've just sort of resampled a single point. Yeah, this might seem a bit odd and a bit arcane. Why did we do this? But you can see right here, let's apply differential privacy. So if you write q on xi equal 1, given q selected by w of x, well, this, just by using differential privacy, is less than or equal to e to the epsilon probability that q on xi is equal to 1, given that q of is equal to what w picked on x prime plus delta. Okay, so right. From here, what we do is we essentially note that, let's try writing this out. We can observe that this quantity is just exactly identical. Oh, sorry, I didn't write this properly. This is equal to w on x prime. We can note that this quantity here that we have here is equal to sort of the opposite case, where q of xi prime is equal to 1, given q is equal to w of x. And this in particular is sort of equal to the expectation. Note that this is kind of independent of this, because remember, this is just a totally, this is not dependent on the data set at all. So you can just write this as, sorry, let me state this again. This is totally independent of x, and in particular, it's can just be written as the following: on D, where q is equal to w of x. The idea is we kind of just swapped out this one sample in order to make it a new sample from the distribution, and that would be representative of the distribution, like sort of the distribution instead of the specific data set. So combining this with the above, what we get now is that, remember what we started with, we have that expectation of q on x, given q is equal to w on x. This is less than or equal to, you just basically substitute this in, and that gives you e to the epsilon times this quantity here, expectation of q of d, given q is equal to w on x, which plus delta. So yeah, this is close, but not exactly what we wanted to prove. Remember what we wanted to prove? We wanted to prove that their difference in absolute value is less than this quantity here. Well, let's see how we do that. Well, one thing we can do is just essentially moving this over to the other side. So what this gives us is that expectation, sorry, let me write it like this. Expectation of q of x, given q equals w on x, is minus expectation q of d, q equals w of x. This is going to be less than or equal to e to the epsilon minus 1 times the expectation of q of d given q is equal to w of x plus delta. And the convenient thing is that this term here is upper bounded by 1, just because it's an expectation of a value that's between 0 and 1. So this is less than or equal to e to the epsilon minus 1 plus delta. So that gives us essentially pretty much exactly what we wanted, except without the absolute value. If you did it taking a look at basically this inequality right here that we did, and do it in reverse, using the sort of differential privacy going the other direction, then that would give you the exact opposite term and allow us to conclude, absolute value is less than e to the epsilon minus 1 plus delta, and that would conclude the proof. So yeah, just repeat this type of argument, except with this inequality in the opposite direction for using differential privacy guarantees. Okay, so what did this lemma say? This lemma said essentially if you do the analysis on the past data set, then it can't possibly give you, if you do it in a differentially private way, it can't possibly give you a query which differs significantly in terms of the value on the data set versus the distribution itself. Cool, so that's pretty much most of the work that we're going to do. Let's just complete it. We'll complete the proof of this as follows. What we're going to do is essentially, we're going to use this lemma, of course, but first we're going to do two things. We're going to do two things. Like, the first thing we're going to do is note first that, okay, which of these should I tell you first? So which method are we going to use for picking queries? So W is essentially going to be the following algorithm. Like, the ugly thing about this type of theorem here is the fact that it essentially looks at the query I, which maximizes the difference between qi and mx of I. So what W will do is it'd be essentially the thing that simulates M on the data set and outputs the query which does this. So W is the, remember W is an algorithm which chooses a query, and it's in particular, it'll choose qi, maximizing this quantity here, q of I of x minus m x I, where I or m is the private algorithm running on our data set, and qi is the ith query. Okay, so the idea is that why is W differentially private? Well, essentially M already does all the work by being differentially private. All you're going to do is just post-process that. So in other words, this is differentially private, just inheriting the differential privacy of the fact that M is differentially private. So yeah, why did we do this? Why did we sort of define this in some funny way like this? Well, the reason is just because we want to really simplify this in order to get rid of this max, and you'll see. Another thing we're going to do to get rid of this absolute value, we're going to do another trick, like basically, which is double the number of queries. So in particular, before we were asking qi from 1 through k, but now we also ask 2k queries, where we also ask, for example, we ask q1 all the way through qk, but also we ask 1 minus q1 and all the way up through 1 minus qk. And these can be answered with the same set of answers. It's kind of use an additional 0 privacy budget, just because literally, what do we do? These ones will be answered, using m 1 through x and so on, but this will be answered using 1 minus 1 m1x. Again, this might seem like a kind of weird thing, but the reason why we do this is so that we have the following guarantee. We do it so that, we have that max of over all I of q sub I of d minus m x sub I. This is equal to max of over all I qi of d minus m x sub I. Yeah, the idea is that you're always going to, if the max was realized by a case where mxi was greater than q sub I of d, then you've now got the negation of it as well in your set of queries. So now you have that, you can get rid of that absolute value. It might seem kind of silly, but if you don't want to think about this, just imagine we did something to get rid of the absolute value, and this is kind of just a clever trick. But once you do this, it's quite easy to see how to complete the proof. All you do is just look at this quantity here. So remember, we're trying to bound the expected max. So what we can do is say expected max of the quantity without the absolute values. Sorry, let me just write it like this. And this is going to be equal to, essentially by doing this, by doing the conditioning, so to speak. It's not actually conditioning, but by saying that this q sub I was picked by this w, then this is sort of an equivalent way of writing it. Just using the fact that the w, like I said, is choosing the qi, which maximizes the sequence. So it just sort of picks out the max difference. The thing we're going to do now is just break this up using linearity of expectations. So this is kind of the difference between what the private algorithm would give on the data set and the what the true query gives on the distribution. So all we do is just break this up, because it's kind of like a triangle inequality type thing here, but there's no actual inequality because we're just using linearity of expectations. Essentially, you're just going to add and subtract how well it actually does on the data set itself. Minus qi of x. And so this is going to be equal to expectation of q sub I d minus q sub I x given q sub I equals w of x plus the other term. Right, and now we're pretty much done. Why is that? Well, let's take a look at what these two terms are. This says that the expected difference between the query on the data set and the on the distribution in the data set is we want to bound this. So this term can be bounded just using our lemma that we had before. So we know this term is less than or equal to e to the epsilon minus 1 plus delta. That's because, again, we know that the query that's chosen here is selected in a differentially private manner. And the second thing just asks, how far off is the differentially private algorithm in terms of error answering the query on the data set itself? Well, by assumption, we know that this is upper bounded by alpha. And this is just, literally here. This is one of the things saying that the algorithm is accurate. So yeah, and that's the entire proof of this transfer theorem. Like you saw, it was rather simple to prove it in expectation. If you want to really do it properly, like if you want to get the full-blown thing that I claimed before, the harder transfer theorem, it's a lot more work, but at least this is a key one that tells you sort of why it works. And the idea is roughly because, you can do the swapping trick and get a new sample from the distribution, and therefore it generalized in the appropriate way. So yeah, it's a very rich and exciting area. People can teach entire classes on it, but at least for today, I just wanted to show you one simple connection, and hopefully if you're interested, you can explore it more.